All right, my friends, section 9.3 is called parametric equations. And calculus. All right, I know you've been wondering where the calculus went. Anyway, so just a quick warm-up for you to consider. Let's say you are given the parametric equations let's see, x equals t squared plus 3t plus 2 and y equals 2t. See if you can find the following. Part A, see if you can find dy dt. Part B, see if you can find dx dt. And then for part C, see if you can figure out what dy dx is. Okay, super good time to stop and pause the video and see how you do. I'll explain this in my own way, and I'm going to take way more steps than I really want you to do for dy dt. I would love for you to just say what the answer is and be confident about it, but this is what might be going on in your head. Dy dt means ddt of y. Y in parametric form is 2t, so that means you're just doing ddt of 2t, and then that would simply be 2, which is why if you just said dy dt is 2 without showing any work, that's why you were right. Dx dt means ddt of x. So that would mean ddt of, and x is t squared plus 3t plus 2, which is why we would say dx dt is equal to 2t plus 3. Okay, now for dy dx, you have more than one way to get your answer here. You could eliminate the parameter. It wouldn't be too horrid. You could say t is y over 2, and then come over here and put y over 2 in. Okay, I lied. It would be a little horrid. Anyway, I did try to give you something that would make you want something other than eliminating the parameter. Which would introduce the first concept of this lesson, which is how are you going to find dy dx if something's in parametric form and if eliminating the parameter is not very fun. And so here's what we're going to do. We're actually going to use dy dt and dx dt to get dy dx. And so this is how. So dy dx is equal to dy dt divided by dx dt. And to make sense of that, imagine just a quick flip and multiply. So dividing by dx dt is like multiplying by dt dx. The dt's cancel and boom, you've got dy dx. So here's what that means. You can get dy dx, and you will get it in terms of the parameter, which in this case is t, but you'll get it. So dy dx is equal to dy dt is 2 divided by dx dt. 2t, so let's make that look more like a t. 2t plus 3, there you go. Okay, and really that's the main point of this first part of the lesson. So we're going to talk about the parametric form of a first derivative. And we're just going to make this piece right here official. So dy dx is simply dy d, in this case the parameter is t, it could be theta or whatever you want, divided by dx dt. Is this something you should memorize? Yeah, kinda. If you're the person that rote memorization does not work for you, then great. So whatever you write, make sure you have something that looks like a rise, see, change in y, divided by a run, change in x. Also make sure that after you write it, a quick flip and multiply, the dt's cancel, and you have this expression right here, and you should be good to go. There are formulas for the parametric form of the second derivative, the third derivative, derivatives of higher order. There are formulas for these things. I personally do not memorize them, and what I'm going to demonstrate is how to fall back on basic principles and know what to do. If you hate that, which I don't think you will, because that's what we've been doing all year, if you hate that, then you get to look up the formula in the textbook and you memorize your little heart out. So let's talk about that second derivative there. So a note, the second derivative of y with respect to x. Let's talk about what it isn't. It isn't, big old not equal to. Sad day, it is not equal to the second derivative of y with respect to t divided by the second derivative of x with respect to t. So I'm just going to say it's not equal to what a lot of people in this moment were hoping it would equal. Let's see if I can use proper notation. Okay, so it's not equal to what most people would hope it would equal, and let's just go ahead, and I know you've missed my caution signs, so let's give you one of those. So I like to put caution signs next to things where there's some common misconceptions or common, here we'll make it cute in color, we'll give you a pink flower this time. I'll give you a little yellow center, and we'll even make the caution sign yellow. There you go. Anyway, common, let's say, educated mistakes, So let's talk about what it is real quick. So d squared y over dx squared. Basic principles, like what do we know about this? So this is equal to d dx of dy dx, right? Like we've known that for a long time. And then if you try to turn that into parametric form, then that would mean that you do d dx of dy dt over dx dt. And then instead of continuing and saying, now this is what this equals, let's just think about what would this mean. When you do this, look at this part C up here. When you do the derivative in parametric form, you get your answer in terms of the parameter. So that would go in here, and then when you do d dx of that, then you'd need to use chain rule to do it, and that's why it's not this simple. And so we're just going to say chain rule would be needed to continue that. Okay, so and then and then you would keep going, but the point is that it's it's not this simple, but it is something that you'll know how to do, and you would not have to memorize a formula for it unless you really want to, and we'll show you what I mean in the next example. Okay, so example 1. Let's have you find dy dx and the second derivative of y with respect to x. Then find the slope and concavity at theta equals pi over 6 for the curve where x is equal to 2 plus secant theta and y is equal to 1 plus 2 times tangent theta. Okay, perfectly good place to pause the video and see what you'll do. Assuming that you've done that, let's start off by finding the easiest thing, dy dx. So dy dx, I did try to give you something where while you could eliminate the parameter if you really wanted to, you probably don't want to. So we will be doing dy dx in terms of the parameter. So dy dx is the same as dy d theta divided by dx d theta. Now let's go ahead and get these little pieces here. So I'll just kind of do this in the form of scratch work. So dy d theta, so we'll just take d theta of both sides here. So that would be 2, let's see, what's the derivative of tangent? 2 secant squared theta. And then dx d theta would be derivative of secant is tangent squared. There we go. So now coming over here and putting that in, let's see, dy d theta is 2 times secant squared theta. Dx d theta is tangent squared theta. I feel like I've messed something up. What's the derivative of secant? Secant squared, are you kidding? Sorry guys, derivative of secant is secant theta times tangent theta. Oh goodness gracious. All right. Okay, secant theta times tangent theta. If you don't use it, you lose it, folks. And let me tell you, even to me every year, it's horrible. Anyway, okay, so the tangents cancel, I would say. So there are a couple of ways you could write your answer and have it be pretty simplified. You could just cancel the tangents out, and you could have 2 times secant theta divided by tangent theta. Sorry, that's a little embarrassing. And then you could simplify it a little more. Let's see, secant is, what's secant? 1 over cosine, right? Tangent is sine over cosine. So you could actually write this as like 2 over sine theta, because like a little flip and multiply type stuff. Or you could write it as 2 times cosecant theta. There you go. So pick your favorite version. You know, you like that one? I don't. This one or this one, totally up to you. And then you do have a rule for dy dx. I'm just going to pick this last one just because. Okay, so there you go. There's dy dx. Now let's go for the second derivative with respect to x. Well, you're always going to have to get the first derivative anyway, so why not just continue on from there? So if I do, then I would just say, hey, if you want the second derivative of y with respect to x, here's how you get it. You take d dx of dy dx. And then let's substitute things in. So that means you're going to take d dx of 2 times cosecant theta. Now notice that you're taking the derivative with respect to x of theta, so you are going to have to use chain rule when you go about this. So let's do that. Derivative of the outside function, so help me. All right, I know you're not here, but let's pretend you are. Derivative cosecant is cosecant negative cosecant cotangent, right? I really wish you were here. All right, negative 2 cosecant theta cotangent theta. So that's the derivative of the outside function, but then you'd have to multiply by the derivative of the inside function. So that would be the derivative of theta with respect to x. Now, what is d theta dx, you ask? I could tell you, but I'd rather that we do the opposite of flip and multiply, and I just want to like point out that we know what dx d theta is. And so I'm going to rewrite this as negative 2 times cosecant theta times cotangent theta divided by dx d theta. So it's the opposite of flip and multiply. It's flip and divide. And then we can substitute dx d theta in. So we're going to put tangent squared theta in right here. So we would have negative 2 cosecant theta cotangent theta divided by tangent squared theta. All right. And then up to you how you want to simplify that. Some people are just so darn proud of themselves that they got to there that they're like, that's it, I'm out. Let's see, but I'm going to, where should I go for my work? I'm running out of room here. Actually, I'm just going to get another piece of paper. So then we could simplify from there. And let's see, how far down did this go? I think we could get this to be as simple as -2 times cotangent cubed theta. There we go. Okay. So there's your second derivative of y with respect to x in terms of theta. Okay. Now the problem also asked for the slope at theta equals pi over 6. And so for that, you'd be going back here and just be plugging in pi over 6. I'm going to take this arrow off. And then just kind of there. So then that would give us dy dx at theta equaling pi over 6. And so that would be 2 times cosecant of pi over 6. Remember, cosecant is 1 over sine. Sine of pi over 6, I believe, is 1/2. So you'd have basically 2 divided by 1/2, also known as 4. So make sure when you answer, you would say dy dx, not all the time, but at this instant when theta is pi over 6 would be 4. There we go. Okay. They also asked for the concavity at theta equals pi over 6. And so that would just be a matter of evaluating your second derivative at theta equals pi over 6. So -2 times cotangent cubed of pi over 6 times. Okay, so cotangent is cosine over sine. So we'd have -2 times, I'll just write -2 over 1 for that part. And then, let's see. I said cosine, right? So cosine of pi over 6 is √3 over 2. Sine of pi over 6 is 1/2, and it's getting cubed. So you'd have -2 times, flip and multiply, you end up with √3, but it is getting cubed. So to simplify that, you could write it as -2 times a 3 and then times a √3, also known as -6 √3. And so d squared y over dx squared, not just all the time, but at the moment when theta is pi over 6, would be -6 √3. There we go. Okay, so is the graph of this function on a rectangular plane concave up or concave down at pi over 6? I'd say concave down. Is the graph increasing or decreasing at pi over 6? I would say increasing since your first derivative is positive. All right, just a little review for everybody. All right, my friends. I think we'll stop here for part 1 of section 9.3, and then we'll do another video for part 2. Take care, everybody.